Hello, and welcome to my talk on intentional data type refinements and their application to the scalable verification of pattern match safety. I'm Eddie Jones, and this work was done in conjunction with Dr. Stephen Ramsay at the University of Bristol. So, what is the pattern match safety problem? Well, it is often convenient to write inexhaustive pattern matching expressions in real applications. That is where some of the possible constructors of an algebraic data type have been omitted. They're not handled, and if the constructors in question were to reach that point in the program, then a runtime error would occur, which we obviously want to avoid. For example, here we have a program which translates arbitrary propositional formulas into disjunctive normal form, a class of propositions which is particularly useful for automated reasoning. It does so by first translating them into negation normal form, which requires that the negation operator only appears in front of atoms. As there are separate constructors for atoms and negative atoms in this formulation, the property is equivalent to specifying that no not constructor appears in the output of the first function. While the type of formulas excludes other data types, the requirement that a formula is in particular in negation normal form cannot be statically expressed or checked to exclude those formulas not from this class. It is possible to create a new data type that represents only those formulas in negation normal form. However, this would complicate the program somewhat by introducing duplicate constructors and requiring additional boilerplate to convert this new data type back into the type of arbitrary formulas when appropriate. Instead, as with most programs, the burden is on the user to ensure that this invariant is upheld. The second function, nnf to dnf, is intended to only take formulas already in negation normal form, and so it doesn't provide a case for the not constructor. If it were to be past one, then it would raise a pattern matching error. We are interested in formally verifying that no such errors can occur, and for this case in particular, that no not constructor will reach the nnf to dnf function. This problem is different from requiring that all pattern matches are exhaustive, as the program would be deemed safe if the first function did indeed remove all occurrences of this constructor by producing a formula in negation normal form. Furthermore, although we are only interested in safety, this problem has a non-trivial overlap with verifying correctness. As I'm sure you'll agree, manually checking this code would be laborious and inaccurate, and there are just two functions here, so we ran our tool and uncovered an error. This is a real screen grab of the warning it produces. Our tool takes a Haskell program as input and returns a constrained refinement type assignment. Any bugs implied by these constraints produce such a warning. As the tool is a GHC plugin, however, it can be directly integrated into the compilation process. These warnings state that a particular constructor might reach an incomplete pattern, and it gives the location of both the constructor's origin and the pattern. In this case, it has spotted a spurious not constructor that should be applied directly to P, but is actually being applied outside of the recursive call to nnf. We model these scenarios through a refinement type system. The idea is that the user will have their own internal model of the data with which they are working. In the previous example, this was an implicit type of negation normal forms, and more precise types for each function, which might be represented with some code like this. From the point of view of the user, the set of available data types has been completed. That is, every refinement which can be obtained by removing constructors has been added to the program. And so in particular, the tool would have automatically added this nnf data type. Note that the code here is just illustrative, and so no such annotations are actually required. The only corresponding restriction is that the arguments to recursive constructors belong to the same refinement. So here we require that OR's arguments are also in negation normal form. Similarly, a conjunction of literals is in this class, as AND's arguments are also a conjunction of literals. On the other hand, the type of clauses, which is a disjunction of conjunctions and literals, is not definable in this fragment, as one of the arguments refers to a different refinement, in this case a conjunction of literals rather than another clause. We refer to these new data types as intentional refinements. We're not the first to consider this problem. However, previous approaches suffer from undesirable algorithmic complexity. They are generally exponential or cubic in some restricted cases. While heuristics do exist for these tools to improve their performance in practice, we instead can make a formal complexity guarantee. Our analysis is linear in the size of the program. Of course, worst case complexity is only part of the story, and especially so when the constant factors depend on several assumptions, which will be discussed in more detail later. However, the GHG plugin we implemented proved very efficient on real packages taken from the Hackage database. Here are some of the benchmarks. And as you can see, even for large packages, the process was completed in the order of milliseconds. We believe this performance hasn't come with a lot of expressivity. Instead, it has been achieved through compositionality. In particular, we maintain precise path-aware exhaustivity checking. That is, when the wider context of some code implies that a path is unreachable, then it doesn't need to handle it, and the tool is automatically aware of that. Furthermore, our analysis is polyvariant, allowing the user to write generic, reusable code while still getting a certificate of safety, which is sensitive to the context of the call site. In effect, top-level definitions can receive multiple types, or an environment-level intersection type, which includes many different usages. So what does this process look like under the hood? Now, don't worry, I'm not just going to talk about typing rules for the next half an hour, but we do need a bit of context before going into design decisions. So there are 3 or 4 important rules in a refinement type system. First, we have subtyping and the ability to cast into larger types. This rule is important as it allows expressions in, say, negation normal form to appear in a position expecting an arbitrary formula, and it is what differentiates a refinement type system from creating new algebraic data types with a separate set of constructors for each invariant. Constructors are typed according to a data type environment delta, which also dictates which data types are in scope and what constructors they have. So we write expressions like delta applied to D applied to K equals T to indicate that the data type environment delta contains the data type D, which has a constructor K, and that constructor has the type T. Data types are eliminated with a typical pattern matching expression. The only difference here is that we require exhaustive patterns where every constructor has a corresponding case. This clearly enforces safety, but it is still sufficiently permissive, as it needn't be exhaustive with respect to the data type environment originally specified by the user as appears in the program text. Instead, the environment can contain arbitrary refinements, such as NNF, and so the second function NNF to DNF is indeed exhaustive. From this perspective, we reduce the task of verifying a program to inferring a latent data type environment against which all cases are exhaustive, if one exists. Finally, to be more precise, one data type is said to be a subtype of another if it has a subset of constructors, and the arguments to each of those constructors are subtypes of one another. One last technical point before we move on to the main content. As previously mentioned, we believe that polyvariance, where functions can receive several refinements, is an important trait in all programming analyses, but especially so when applied to functional languages, which tend to be structured around a small number of generic combinators. For the purpose of translating formulas into disjunctive normal form, the first typing of NNF is sufficient. It expresses, at the type level, that given an arbitrary formula, the output will be in negation normal form. However, it is also true that it preserves formulas which are a conjunction of literals, and similarly, a disjunction of literals, along with several other properties which may become relevant in different parts of the program. Clearly, none of these typings are best, and they are not mutually derivable. So it is therefore necessary to consider a larger set of data types, which can be refined independently of one another, rather than refining each data type once for the duration of the program. To this end, we rephrase the setup as typing with respect to the sum of all possible refinements, which we refer to as the completion or canonical environment, and indicate it as delta star. Its data types are injections from disjoint environments, thereby restoring a separation of concerns between different refinements. Instead of an NNF data type, we now consider the type of formulas refined according to the NNF environment, which is an isolated part of this completion. The declarative type system allows for variables to have multiple types in the environment, which you can think of as a restricted form of intersection types. For the purpose of type inference, however, functions are considered polymorphic over constrained data type environments. The shape of this type is completely determined by its unrefined type, that is a function from formulas to formulas, but with fresh refinement variables associated with each occurrence of a data type. Remember, these variables refer to possible data type environments, not the data types themselves. This type acts as a template, which is then constrained according to the function's definition. The different solutions to those constraints, which are generated by type inference, are assignments of data type environments to these refinement variables, which then corresponds to the different components of the function's intersection type. Sort of constraints which inference gathers are fairly typical set constraints, a well-established technique from program analysis. As the refinement variables range over data type environments, however, rather than constraining them directly, we constrain the data types which appear within them. The constraints therefore concern explicit sets of constructors and the subset of constructors which appear in a data type environment. These latter sets we indicate as, say, X applied to the formula data type, in line with the use of the data type environment delta from the typing rules we just discussed. Returning to our NNF example, the first two cases imply that if AND can appear in the input, then it can appear in the output, and similarly for OR. The corresponding constraints are conditional. They consist of an inclusion constraint, for example, that the constructor AND can appear in the refinement variable Y, which represents the output, as indicated by the type of NNF. But there is also a guard that encodes the path from which it originated. In this case, the AND is in the input, which is represented by X. The solutions need only satisfy the constraint's body if it satisfies its corresponding guard, which creates a path-sensitive analysis. The third constraint here ensures that the function is exhaustive. That is, all possible constructors in the input have a corresponding case. Translating the negation of a formula constitutes its own subroutine. So suppose we've refactored that part into a separate function, which is also going to be polymorphic over its own refinement variables. Here you can see in the not case that we've called out to a second function, which has a similar set of constraints that encode De Morgan's law, that AND and OR have been swapped. When we call this auxiliary function from NNF, naturally these constraints must also apply. However, polyvariance requires that we create fresh refinement variables that don't lead to any interference. Here we have represented them as Z prime and W prime, respectively. These variables will naturally be refined according to the auxiliary function's constraints, which is why we have this duplicate set of constraints. Although they are also conditional on not appearing in the input environment X, as it is only within this branch that the NNF not function is called. Furthermore, we must relate these fresh refinement variables to its usage context. In particular, that the program variable P is a valid input for this instantiation of NNF not, and that its output can serve as an output of NNF. These requirements correspond to the constraints that X formulas, which are associated with the input and in particular the expression P, are a subset of Z prime formulas, which are going to be the input for this particular instantiation of NNF not, and that W prime formulas, which are the output of NNF not, are a subset of Y formulas, which is the output of NNF. These new constraints give rise to an important distinction between intermediate and interface variables. Interface variables are those which appear in the function's type, in this case X and Y, and are therefore subject to instantiation at future call sites. Intermediate variables, on the other hand, such as z prime and w prime, correspond to points in the body of the function other than its input and output. Exposing these variables to a caller not only breaks abstraction, but also quickly leads to an issue of performance. Suppose, for example, we have n top-level definitions or mutually recursive groups. Then in the worst case, we might have a dependency graph which looks something like this. We should assume that these functions are limited somehow in complexity, that there is a maximum depth of subterms. In which case, the number of constraints produced by inference when analyzing the first function will be a constant, k. The second function will again produce k of its own constraints, but it might also call f1 and so duplicate those constraints, creating 2k in total. This is not because it's more complicated, but the variables, which in f1 cannot be associated with any constraints, can now be associated with the constraints from f1. So it has more constraints even though it's not more complicated. Similarly, the third function may call f1 and f2, but will produce k constraints of its own. So there are 4k constraints associated with just this function. And the problem gets exponentially worse for larger programs. This approach is highly non-compositional, as for each function, in essence, we have to reanalyze everything that came before it because we have a duplicate set of constraints. And while set constraints can be solved in linear time, any reasonably sized program will produce far too many to be practically verified. So what went wrong? While it is fair to say that this exponential blow-up is an inherent feature in constraint-based analyses, as we have made very few domain-specific decisions up until this point, at the same time, some of the most stable and efficient type inference systems use constraints, such as Hindley-Milner. Unlike the system we just presented, Hindley-Milner relies heavily on the ability to simplify constraints. This process of normalization deals with the problem of intermediate variables. For example, in pure Hindley-Milner, we can use the existence of a most general unifier to instantiate intermediate type variables in terms of those of the interface. That is, those which appear in the top-level type signature. In languages such as Haskell, type class constraints can be deterministically reduced to some minimal form, such as replacing the equality type class constraint on lists with a constraint on the type of its content. Importantly, these reductions don't lose any information, so it is possible to recover any valid assignment to the intermediate variables. This is sometimes referred to as constructing a guess-free solution. The advantage of eliminating intermediate variables is that the number of constraints is then limited by the number of variables in the type rather than the number of top-level definitions on which it depends or the complexity of the function definition. We therefore seek an approach that limits constraints to those concerning interface variables and thereby restoring compositionality. In the context of subtyping, the most natural method of simplification is to replace a variable with its bound. If it only occurs in a positive position, for example, we can replace it with its lower bound and vice versa. However, this is not so simply done for algebraic data types in general. Consider the following worryingly simple scenario that illustrates the importance of our intentionality restriction. The tail function, which is the complement of head that skips the first element of the list, has been given the type inject y list of A to inject z list of A, which is constrained such that the input y only contains the cons constructor, that the list is non-empty, otherwise the tail function is undefined. Remember, these refinement variables stand for data type environments, so they can also assign constructors types. In this case, the arguments to the cons constructor in y is the type of the output, z. This makes sense as the tail function will return the argument to the cons constructor. Our fragment doesn't cover this case, as recursive occurrences are from a different environment. That is, it's a non-intentional environment that we're defining here, which is why this constraint deviates from the previous forms. It's just illustrative. Requiring that this argument is also refined according to y rather than a new environment z would only lead to infinite lists being considered. So it's not a sufficiently precise example type for tail. Now consider the fixed point of tails, which produces an error for non-infinite lists and doesn't terminate otherwise. Its constraints will contain just 3 refinement variables, a variable which appears in the interface, x, and 2 variables we are trying to eliminate, y and z, which arise from the call to tail. In addition to tails constraints, we have that the input x must be a suitable input to tails, i.e. that the constructors which appear for the input appear for list of a in x is a subset of those which appear in y. And the output of tails, which is refined according to z, can be returned from f. So z is a sub-environment of x for list of a. As y appears as an upper bound of x, we might be tempted to instantiate it with its upper bound, the list containing just cons. And similarly, z has no lower bound and appears only as a lower bound for x, so the empty set seems an appropriate instantiation. This partial solution can be seen on the right. These two constraints can be passed as saying that the list refined according to x contains only the cons constructor, which is what we might expect from the fixed point of tails. However, if z is empty, then y doesn't actually have an accessible cons constructor, as there is no value of type inject z list of a, which is its second argument. Therefore, as the original constraints require that x is a sub-environment of y for lists, x can't have an accessible cons constructor either. It must in effect be empty, and in particular, doesn't contain any infinite lists. These new constraints don't capture the same set of solutions as the original, even though we seemingly made no arbitrary choices. It is clear that these constraints are not yet in a suitable normal form, as there is still some restrictions on the solution space which they don't explicitly represent. While subtyping for functions is easy to normalize by replacing this bottom constraint with the top two, fully expanding the subtyping rule for data types would create an infinite set of constraints in the presence of arbitrary recursion, as at each level there may be a different and indeed new refinement variable. To be most general, when we unroll a data type according to the subtyping rule, we must generate a new refinement variable if we don't want to pre-impose any shape onto the data type environment. That is, of course, without our restriction, which requires that recursive constructors belong to the same refinement environment. Under our restriction, it is just the same variable at each level, which we can finitely saturate to ensure that any implicit connections are explicitly represented in the set of constraints. Having now motivated the requirement placed on intensional data types, we can return to the task of eliminating intermediate variables and solving the inferred constraints. First, we add any implicit constraints from the data type environment by that unrolling process. To be more precise, each data type has what we call a slice. This slice contains every data type needed to understand its definition. Those are the data types that appear when we unfold a data type by moving to its constructor's arguments. For example, formulas cannot be constructed without literals, so they appear in its slice. Thus, we also constrain the literals according to these refinement variables, even though they don't explicitly appear in the original constraints or program. This mitigates the previous issue where the constraints didn't accurately represent the set of solutions. Next, we saturate the constraints. This process is a generalization of the transitive closure and a particular instance of Horn-Clause resolution. These two new constraints, which could be deduced from the previous set, are added to serve two purposes. First, it decides if there is a satisfying assignment, as a contradiction would be uncovered otherwise. That is where a constructor must appear in the empty set, which is clearly unsatisfiable. And second, it propagates any remaining constraint information from intermediate variables to those in the interface. This final set of constraints is sufficiently verbose so that constraints concerning intermediate variables may be soundly discarded. At this point, the constraints concerning intermediate variables don't add any information to the overall set. They can be solved in a guess-free manner by merely solving those concerning the interface variables. For the purpose of describing valid instantiations of the interface, we have to retain all constraints concerning interface variables, but we can cross out the others. We refer to this process as the restriction. Recall that the interface of NNF contains only the variables x and y, and so only the constraints that concern just these variables remain once we remove these constraints. What difference does this make in practice? While in the benchmark packages, the number of intermediate variables was typically in the order of tens of thousands, compared to just tens of variables appearing in the type with the largest interface. So it is quite a severe restriction. Furthermore, as with the inference systems we discussed earlier, any solution to the remaining constraints can be extended to the original set in a guess-free manner. That is, any solution to the interface variables can be extended to a solution including the intermediate variables. Note that this is only achievable through our intentional restriction. Interestingly, this can be done for any subset of refinement variables, not just those appearing in the functions type, and that the extreme case corresponds to the existence of a minimal model from the theory of horn clauses. Of course, we don't want to restrict beyond the variables appearing in the interface, as this would limit possible instantiations at call sites, as we've implicitly chosen some instantiation of variables which did not need to be instantiated. Let's now revisit our complexity argument. The constraints produced by each top-level definition are limited by the number of refinement variables of the type, which we shall again assume has a constant upper bound. As we saw even for extremely large packages, the interface didn't go above 50 variables, and this corresponds to a combination of the number of data types and the number of constructors, which we shall assume doesn't grow with the number of top-level definitions. Furthermore, by assuming a limit on the size of the type, there is also necessarily a limit on the number of constraints concerning those intermediate variables. Sorry, the interface variables. While we must saturate these sets, a process which is in itself exponential, inference is now compositional, as the number of constraints associated with a given top-level definition is independent of the number of its dependencies. It follows that the overall complexity is linear in the size of the program. Requiring data type environments to be intentional unfortunately doesn't cover some common cases, such as non-empty lists that we saw earlier. However, the problem of infinite descent can be solved by any number of fixed shapes. For example, unrolling data types by one step would cover singleton containers. We can refine this first data type to not contain the empty list without affecting recursive instances, as it refers to a different data type. So it doesn't have to just contain infinite lists, it could contain specifically non-empty lists. Importantly though, this new environment is still finitely saturating, as it is eventually intentional. We plan to investigate how a range of data type shapes can be uniformly integrated into our tool, while retaining compositionality and requiring few, if any, annotations. Thanks for listening. I hope you enjoyed the talk.